So we now know the diagonalization process. So whenever a matrix is given, and if you're lucky, so that you can find n linearly independent basis of eigenvectors, then you can diagonalize your matrix. But that is not always possible. So especially when your eigenvalues have some algebraic multiplicity is greater than 1, then you will need to check if the geometric multiplicity and eigen is a geometric multiplicity and the algebraic multiplicity of that eigenvalue agree. So if not, then you cannot diagonalize the matrix. Okay, so and today we'll discuss some minor applications of the matrix diagonalization, mainly about the powers and product. Basically, I'm going to talk about the matrix powers and matrix multiplications. So, suppose that you have two n by n matrices, then how many multiplication do you need to multiply these two matrices? So, in order to compute a single entry of the resulting matrix, then you will need to multiply n times, right? And since there's n square such entries, so therefore you will need n cubed, so n to the third many multiplications just in order to perform a single matrix multiplications. So I say matrix multiplication is a big deal, so because it requires many. So there is actually a very clever algorithm which requires even less than n to the third many multiplications, but that is not the main topic for today's course. And also on top of that, so how many multiplications do you need just to compute a to the k's power? So a k is an integer greater than or equals to 1. Then, if k is getting large, then number of multiplication would be also getting large. So therefore, such a computation is not usually feasible. But the problem is, for many practical purposes, then from time to time, you are supposed to compute the a to the k's power. So how are you going to do this? So today, I'm going to tell you a very nice algorithm to compute the a to the k's power, especially when a is a diagonally eligible matrix. So I will begin from some basic stuff of the eigenvectors, eigenvalues. If you have, suppose that you have n eigenvalues of A, then if you take the k's power of the matrix A, then all these eigenvalues raised to the same power, they're going to be the eigenvalues of the A to the k's. The proof is very simple. Maybe why don't you take I'm going to give you a couple of seconds to read the proof, and then I guess that will be enough. Okay. Okay, great. Okay, done. What about next? I have a non-singular matrix S. Sorry. I have a matrix. Sorry. Let me correct myself. A is a sum matrix. I guess A is a diagonalizable matrix with diagonalized by the non-singular matrix S. So S inverse times S times A times S is some diagonal matrix. Then the same set of vectors, so the same set of eigenvectors will diagonalize A to the K's. Okay. Well, proof is also simple. If this is the diagonal matrix lambda, then this one has to be sorry. Okay. Okay. Right. So whenever you take the case power of this, then you know what I mean. So then S inverse times A to the case S is the diagonal matrix. Okay. The next, A is a non-singular matrix and lambda is an eigenvalue of A. Okay. So and I think in this case lambda cannot be 0. Why? Because if any matrix has the 0 as its eigenvalue, then that implies the matrix must be a singular matrix. So lambda is a non-zero vector. Lambda is a non-zero number, guaranteed. Therefore, and it says the A inverse has an eigenvalue of 1 over lambda, which is the reciprocal. Also, proof is very easy. Just take some time and read the proof. That's it. Okay. So these first 3 propositions are about the power of A, and now we'll talk about the product of A and B. Suppose that I have 2 matrices, A and B. A and B, and let us suppose that they are both diagonally eligible matrices. Sorry. And if A and B have the same set of eigenvectors, sorry, I made another mistake. Eigenvectors. Then A times B is B times A. So, well, in other words, well, they commute. So, well, the matrix multiplication usually do not commute. So A times B is not the same as B times A in general. So, but however, in that case, so they actually commute. Okay, so what do I mean by the A and B have the same set of eigenvectors? They both have the same set of eigenvectors, means they are diagonalized by the same non-singular matrix S. So S inverse A times S which is the diagonalization of the matrix A. The second line is the diagonalization of the matrix B. Then A times B. Sorry. Then A times B is S times lambda 1 S inverse times S times lambda 2 S inverse, which is this. But 2 diagonal matrices, they can commute. They always commute, right? So lambda 1 times lambda 2 is lambda 2 times lambda 1, and therefore this guy should be B times A. Okay, great. And in fact, the partial converse of the above proposition is also true. Well, again, let us assume that A and B are both diagonally eligible matrices, and I am putting some additional assumption on that. So I assume that A has n distinct eigenvalues. So A is a n by n matrix, and it has n distinct eigenvalues. That implies that every eigenvalue of A has geometric multiplicity equals to 1. Okay, they are all one-dimensional spaces. So now it says, suppose that A and B they commute. Then A and B have the same set of eigenvalues. So eigenvectors. Sorry. So, okay, so this is kind of some sort of not complete converse, but some partial converse of the above proposition. Okay, so what about the proof? Suppose that X is an eigenvector of A with eigenvalue lambda. So now let us consider A times B times this eigenvector. But since A and B they commute, so which is the same as B times A times X. But A times X is lambda times X because that is the eigenvalue, it's eigenvector. So it's lambda times Bx. So A times Bx is some lambda times B times Bx. So this implies that B times X, this is another vector. This one also has to be an eigenvector of A with eigenvalue lambda. Okay. Now, so for this eigenvalue, so this is an eigenvalue of matrix A, and it has the this is a one-dimensional vector space. This is eigenspace. Okay. So Bx also must be some scalar multiple of X, right? So what does it mean? So therefore, X is the eigenvector of B. Okay. Okay, great. Okay, good. Actually, I can try even more than that. So the above proposition is also true even if we drop the condition of A being n distinct eigenvalues. So that means if A and B are both diagonal algebra matrices, and then A and B commute if and only if they share the exactly same set of eigenvectors. Same mistake. How do I prove this? Well, I really try to find a very nice proof that is within our scope of interest, but well, I failed to find one. So the easiest proof that I can find is using a minimal polynomial, but I have never introduced such a thing in this course. So I am not gonna prove this final statement. But well, this is also very nice to know. So well, especially if you're interested in some quantum physics, then this fact might be useful later on. So diagonal algebra matrices, and being able to commute is if and only if they are. So sometimes we say A and B have the same set of eigenvectors. Sometimes we say they are simultaneously diagonalism. Okay. But if A and B are not diagonal algebra matrices, then this statement might not be true. So this condition is very essential. Okay. Okay, great. And now I will be turning to section 5.3, difference equation. Equation and power of a. Okay. what is a difference equation? Have you ever heard what difference equation is? I guess most of you have heard about the differential equation. Differential equation in Korean, 미분방정식. But this is difference equation. So what is difference equation? What is actually difference between those two concepts? So I'll try to explain in today's lecture. So, so if a differential equation is a equation about a function, the solution of differential equation is a function, but the solution of the difference equation is not a function, so is not a continuously real value function, but the solution is a sequence. So difference equation is very simple. So differential equation is some sort of recursive relation. So just let me go back to the calculus 101. So, and the sequence was very big topic in that course. Do you remember that? And there were two ways to define there were two different ways to define a sequence. So the first one is just give you some explicit closed formula for the sequence. And the next one is they try to give you some relation between some neighboring terms of the sequence. Like 8n plus 1 is 2 times an. Then can you guess what your sequence is? Then in that case, your sequence an must be some constant multiple times 2 to the n, right? That is what we say the recursive relation. So difference equation is a equation about a sequence. So an minus 1, an minus 2, an minus k, they are all terms of the sequence. And difference equation is going to give you some relation between some terms between the sequences. Terms of the sequences. Then from this information, you are supposed to find a closed formula for the sequence an. That is a difference equation. Okay. Okay. So whenever a difference equation is given, there are many difference equations. So in the world of differential equations, there were a linear differential equations and there were nonlinear differential equations. Same is true for in the world of the difference equation. So there are linear difference equation and nonlinear difference equation, but this is the linear difference equation. This is the easiest difference equation. So linear difference equation with constant coefficient, and since an is depending all the terms up to n minus k, so we say this is a difference equation of degree k. It's just name, just you can't forget. So the question is, whenever this difference equation is given, can you find a closed formula for the sequence an? If you can find such a sequence an, then we say you solve the difference equation. So this is going to be, if you can find such a closed formula, then you solved that difference equation. Okay. Of course, you can find the closed formula just by using this information only. So in order to find the closed formula, then also you will need to know something about some initial terms. Since an was depending on from an minus 1 to an minus k, so in that case, in order to completely determine an, you will need to know a0, a1, a2, up to ak. So then you can determine, right. So sorry, so up to an minus 1. So whenever you have such an initial condition, then you can completely determine a closed formula for the an. So this is a difference equation. And today we are interested in solving such a difference equation. This is actually my personal belief, but this is my own idea. But I believe difference equation is as important as the differential equation. Why? The computers cannot deal with the continuous function. For computers, because the computers do not understand the function. What computer can understand is just bunch of table. For any given input values, it has the output values. So they only know, so in computer, everything is considered discrete manner. Therefore, every continuous function can be translated by some sequences. And solving differential equation for computer is the same as the solving a difference equation. Okay, so difference equation is as important. So in that case, in that sense, so I claim the difference equation is also very important. And we are interested in finding the solution. So we want to solve the difference equation. And the probably the most important example of the difference equation is a Fibonacci sequence. So, have you ever heard about the Fibonacci sequence? So Fn is the sum of Fn minus 1 and Fn minus 2. And there, so, and also initial conditions is the initial conditions are F0 equals to 0 and F1 equals to 1. So from this given information, you can actually determine Fn for any integer n. But can you find a closed formula for Fn? Have you ever tried this problem before? Like when you were in high school student? Did you? Have you? No? Yes? Maybe? Okay, so if you have never solved such a difference equation, then I will try to solve this. Okay. So we are interested in solving this kind of difference equation. Actually, we're gonna do even more than that. By the way, this is a difference equation of degree 2 because it depends. So Fn depends on from Fn minus 1 to Fn minus 2. So, but instead of dealing with a single difference equation of degree k, but we are interested in solving a system of difference equations. Sorry, think things are getting more and more complicated. So what is this? So I have n sequences from u1 to un, and the k plus 1's term of the un is depending on the u1, the k's term of the u1 and k's term of u2, up to k's term of un. And same thing is true for this and this. So this is not a single difference equation, but this is a difference equation for u1 to un. So I say this is a system of difference equation. Okay. Then and also every k plus 1 term is depending on the case term, just previous term, case term of u1 to uk. So I say this is difference equation, system of difference equation of degree 1, right? Okay, so we are interested in solving this difference equation, and okay, as you will gonna see later on, but so being able to solve such a system of difference equation of degree 1 will enable you to solve any single difference equation of any degree k. Okay, this is what you're gonna do. This is what you're mainly interested in today's lecture, and I've got better ways writing this. So, well, writing down, persisting on this notation will be time consuming. So instead of doing this, I will change this left-hand side as a column vector from u1k plus 1 to un_k plus 1. And they are all some multiples of the constant and the case terms. So maybe why don't you write this guy as an n by n matrix times this column vector. Okay. So, and from now on, we're gonna write the vector uk is a times uk. So, well, this A is a called n by n matrix with constant n by n matrix with constant entries, consisting of A11 to ANN. So this is what my matrix A, and this guy, this column vector, the case term of each of these sequences. So this I will call U sub k. Therefore, this guy should be UK plus 1. Okay. So this is going to be my notation from now on. Okay. So this is our difference equation. And having just a difference equation is not suffice to solve the difference equation. So in order to completely determine your solution, then you will need to have a initial condition, the first term of each of these sequences. So which I will say from U10, U20, UN0, which I will call U sub 0. And this guy will be called an initial condition of the difference equation. Okay. Okay, great. Now, question. For these given informations, I think I can find a closed formula for the system of difference equation. What is, can you guess? Then UK is actually A times A raised to the power of K times U0. Okay. Agreed. So for this given difference equation and this initial condition, this one must be the one and only solution of that difference equation. Right? Right? Okay. Solving difference equation is very good, very easy. Nothing to worry about. But no, well, actually, there is a problem. So you are supposed to find the closed formula for UK, right? The question is, how would you compute A to the power of K? This will be too much, this will be so time consuming. I mean, the question is, so therefore, being able to solve such a difference equation is the same as being able to find the closed formula for A to the K. But as I told you before, the computation of A to the power of K is usually horribly complicated. So how would you do this? Well, in general, so there is no easy way to compute A to the power of K, but if suppose that A is diagonalizable matrix, then everything is becoming so much easier. Suppose that A is diagonalizable matrix. Then, well, so I have diagonalized the matrix A and solving this equation for A. So A is m times lambda times n inverse. Then therefore, a to the k is m times lambda to the k times m inverse. Okay. Now, computation of a to the k is not, well, will be complicated, but computation of the diagonal matrix, the power of k, should be super easy. Okay. So which is, this is actually m times, this is the lambda to the power of k, raised to the power of k times m inverse. So therefore, the solution of the differential equation uk is, which is a to the k times u0, which is n times this diagonal matrix, but everything, every entry has been raised to the power of k times m inverse times u sub 0. Okay. 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 So, and well, and for simplicity, so I will say, so I will define the column vector C is m inverse times the initial condition, so which I will denote from C1 to Cn. Then UK is going to be m times this diagonal matrix times this matrix C. Okay. But you know what the matrix M is. The matrix M consists of color eigenvectors. Eigenvectors is columns. So this one, so x1 from xn, they're going to be the eigenvectors of the matrix A. So times this diagonal matrix times these things, this constant from C1 to Cn. So expanding this, this is simply going to be C1 times lambda 1 to the k x1, C2 times lambda 2 to the k x2, Cn times lambda n to the k times xn. So that's it. So this is a complete solution of, this is the solution of the system of differential equation. And I believe this is the closed formula for UK. And by doing so, I solve the equation. I solve the difference equation. Okay. Okay, great. I really like it. So, and okay, so now we know the theory. So why don't we just take time to then go back to the Fibonacci sequence and try to find the closed formula for the Fibonacci sequence? So Fibonacci sequence, I have fn plus 2 is fn plus 1 plus fn and f0 is 0 and f1 is 1. Okay. Well, this is a single difference equation of degree 2. Now, what I want to do is I want to change this guy into a system of difference equation of degree 1. So how can I do that? So actually, there is a very clever idea. So fn plus 2 is fn plus 1 plus fn, and fn plus 1 is just fn plus 1. So this is tautology. It doesn't contain too much information, but by doing so, now I can make this guy as system of difference equation of degree 1. So fn plus 2 and fn plus 1 is one, 1, 1, and 0. And fn plus 1 and fn. Okay. Okay. Now what? Now we let our solution UK to be this guy. Okay. Then this relation, then this equation is going to be UK, the left hand side is UK plus 1. Okay. Is the matrix times this. Never mind. UK. So, well, for convenience, I will call this matrix A. Okay. Okay. So what I want to do is this. I will try to solve the system of difference equation of degree 1, and I'm going to pick up the second. So, well, once I solve the system of difference equation, then I'm going to only choose the second component of the UK. Then that will be the solution of my original problem. Okay. Okay, so I have the problem has been set up. My matrix A is 1, 1, 1, and 0. So first, I will try to diagonalize this matrix if possible. So determinant of A minus lambda I is 1 minus lambda times minus lambda minus 1. So this is lambda square minus lambda and minus 1. Then the solution is lambda 1 is 1 plus square root of 5, everything divided by 2, and the other one, which I will call lambda 2, 1 minus square root of 5 and divided by 2. Oh, this is sometimes we say this is a golden ratio or whatsoever. And well, this is a tedious computation, so I don't want to spend too much time computing these eigenvectors. And the first eigenvector of lambda 1 is this, and the second eigenvector is that lambda 2 sub and 1. All right. So UK is C1 times lambda 1 to the K and lambda 1 and 1 and plus C2 times lambda 2 K and lambda 2 and 1. So all I need to do is just determine these coefficients C1 and C2. So C1 and C2 is this column vector was determined by the initial condition. So M inverse times U0. So this is, so what is M? So M must be lambda 1, 1, lambda 2, 1. This is my matrix M. And I am supposed to invert this And the initial condition U0 is, hey, wait, what was my UK then? This is my UK. So, oh, sorry, I messed up. Okay, sorry, I messed up. And since this is my UN, so U0 should be F1 and F1 F0. So what was F1? F1 was 1 and F0 was 0. So 1 and 0. Okay. So, and this is also very tedious computation. So it turns out this is 1 and minus 1. So my C1 is just 1 over square root of 5, and C2 is minus 1 over square root of 5. So therefore, UK is 1 over square root of 5, lambda 1 to the K. Okay, so okay, so this is the answer. And so what is my Fn then? And so Fk is the so I should be picking up the second component of this matrix. So this vector. So 1 over square root of 5 times so-called the golden ratio raised to the K minus okay. So this is going to be the closed formula for the Fibonacci sequence. Great. So if you have never had this kind of computation before, then maybe this is nice time to memorize this. But everything is so straightforward. There's nothing to memorize. Just understand the diagonalization and the. Well, also I learned a very interesting fact. So this number 1 minus square root of 5 divided by 2. This is a number between minus 1 and plus 1. So as k is getting larger and large, so this term actually tends to 0. So eventually, Fibonacci sequence is increasing as much as an exponential function. Okay, good. There is another very interesting example. The Markov matrix. The problem goes like this. Sorry. Such a problem arises very often. So in stochastic process, well, let us consider this hypothetical scenario. Well, I have a city, so I'm going to call it the city A. I have city A, and Yn is the number of people living outside of city A in nth year, and Zn is number of people living inside of city A in the nth year. So these are the number of populations. in or out of the city A. And let us consider this. Well, there is no the entire population, it just remains the same, but every year 1/10 of the people living outside of city A moves into the city. And also at the same time, every year 2/10 of the people living inside of city A moves out from the city. Okay. So the question is, can you figure out the number of population in nth year? Just provided these two information. So let me try to figure it out. So I did my best to describe this situation scenario into a single matrix equation. So the population in n+1th year, n+1st year should be depending on the population of the nth year. Therefore, the population living outside of city in n+1st year should be 1 times 9 or 0.9 times yn plus 0.2 times zn, right? Because 1/10 of the people, so it's gonna lost 1/10 of these people. So 0.9 times the original population plus the 2/10 of the people living inside the city moves outside of city. Therefore, this much of population should be added. And likewise, Zn plus 1 must be 0.1 times Yn plus 0.8 times Zn. So translating everything into the language of the matrix, so I can compactify the expression like this. Okay. All right. Okay. This matrix is called the Markov matrix. There is a very interesting property in this. So in this matrix, the first is every entry in this matrix is always non-negative, and the sum of for every column, sum of its entry is always equals to 1, right? This guy plus this guy is 1, and this guy plus this. So this is what we say the Markov chain. So Markov chain consists of the bunch of vertices, a bunch of state, and for every transit for every turn, the population on each of these vertices just moves in or moves out from one vertex to another. So in that case, can you figure out the population in nth year? So nth turn. So that is very typically asked question in the Markov chain process, Markov chain problem, and this is one such example. Okay, so what is the solution of this? Well, but there's nothing to worry about. This is still a degree 1 difference equation, and you know how to find the solution. Okay. So in this case, Yn Zn is this Markov matrix raised to the nth times the initial population y0 and z0. Okay. So I think this is the right time to give you the definition of the Markov matrix. So what is the Markov matrix? And we say an n-by-n matrix is a Markov matrix if it satisfies two conditions. The first, every entry must be non-negative. And the second, the sum of entries of every column should be 1. So this is the condition of the Markov matrix. So this is a clearly oh sorry. Where is it? So this is clearly a Markov matrix. So let me try to find the solution of this problem. Well, the solution is very simple. First, we need to diagonalize the Markov matrix A. We diagonalize the matrix. Well, so spending enough time and effort finding and solving the characteristic polynomial. So I can find two eigenvalues, lambda 1 and lambda 2. So, and whose eigenvector is 2 and 1. And its eigenvector is 1 and minus 1. So yk and zk should be c1 times 1 to the k, 1 to the k times the first eigenvector 2 and 1 plus c2 times 0.7 k and 1 and minus 1. So I need to determine the constant C1 and C2. C1, C2 is, this is my matrix, 2, 1, 1, minus 1. This is my M, and inverted, and initial population was, I don't know. So I would just simply say Y0 and Z0. So, and the answer is 1/3 Y0 plus Z0, and another 1/3 Y0 minus 2 times Z0. So, and okay. So this is the solution. Okay, great. Just one more thing to add. What happens if k goes to infinity? I mean, so I want to find. So I really want to see. In that case, if the really want to see. So if the population stabilizes or not. So in this scenario, as k goes to infinity, this vector clearly tends to 0. So I can simply get rid of this. Therefore, it implies that as k is getting large, the population, so yk, so this yk. So yeah, the population living outside of city is gonna be the entire population, 66% of the entire population. Okay, and the population of people living inside of city should be 33% of the entire population. Okay. So this one we call a stable solution or asymptotic solution. So if k goes to infinity, yk and zk is so this is called asymptotic solution or stable solution. Now we have very interesting. So now I just came up with very natural question. That is, for any Markov matrix, do I have such a nice asymptotic solution? Maybe there can be. Maybe there you might be able to imagine some Markov matrix which doesn't have any stable solution at all. Or sometimes, is there any Markov matrix so that the population goes to infinity as k goes to infinity? Oh, I don't know, maybe unlikely. So there is very interesting theorem regarding the Markov matrix, which goes like this. Suppose that I have Markov matrix. Then, well, the first interesting case also theorem statement is, for every Markov matrix, one is always a and its eigenvalue. So that means it always has at least one stable solution. And other eigenvalues have the magnitude which is less than or equals to 1. So if there is at least another eigenvalue whose magnitude is 1, then there may be that Markov system, that Markov process will not stabilize, may not stabilize if there is another eigenvalue whose magnitude is 1. But the number 3 says, if every entry of A is positive, then there cannot be any other eigenvalue whose magnitude is 1. I mean, in other words, in this case, every other eigenvalue has magnitude strictly less than 1. So that means, in that case, as k goes to infinity, all these other eigenvectors, they just tends to 0, and only this eigenvector survives. Okay. So I will prove this. The number 1, we consider A transpose, then A transpose, let me multiply a vector. Oops. Let me multiply a column vector whose entries are all 1s. Then, what do you think is the answer? It's just the same thing. Why? Because, well, A is Markov means that sum of every column, sum of entries of every column should be 1. Therefore, for A transpose, sum of entries of every row is also going to be 1. Therefore, multiplying this guy by this, the first entry must be also 1, and second entry also must be 1, like this. So what do you know from here? So A transpose has eigenvalue 1 with eigenvector 1, 1, 1, 1, 1. Okay. So 1 is an eigenvalue of A transpose. But you know that the determinant is invariant on invariant under transpose. Therefore, if A transpose has eigenvalue 1, then A also must have eigenvalue 1. Determinant of A the characteristic polynomial of A transpose is the same as the characteristic polynomial of A. So A has 1 as its eigenvalue. Yeah, so this is number 1. What about number 2? All the other eigenvalues have magnitude less than equals to 1. So, in order to see number 2, we have to make sure that the product of two Markov matrices is going to be another Markov matrix. Why? If A and B are Markov, then AB is Markov. Why is that? So since every entry of A and B are non-negatives, therefore every entry of A times B also must be non-negative. That is which is obvious. So all we need to see is the sum of the entries of every column. So we need to make sure that it should be always 1. So A I K B K J. This is the component of the J's column of the resulting matrix AB. Okay, and I am taking the summation from I from 1 to n. Therefore, if I can show that this guy equals to 1, then I'm pretty sure that this is a Markov matrix. But this is the summation, double summation. So I am always good to exchange these two summations. So from I1 to n, AIK and BKJ, right? But this is what? So this one, this summation is I is varying from 1 to k, but this number also must be 1, right? Because A is Markov. Therefore, for every column of A, the sum of this entry must be 1. So therefore, this guy should be 1. So this is just K1 to N, BKJ. But since B was assumed to be Markov, so this one also must be 1. Okay. So therefore, if A is Markov, then A to the k's power, A raised by k's power also must be the Markov matrix. So every positive power of AK is Markov. Now, suppose that A has an eigenvalue whose magnitude is strictly greater than 1. I would say lambda. Then lambda k is an eigenvalue of ak. Okay. Let B be a unit vector, unit eigenvector of lambda k of matrix AK. Then A K V is lambda times V. Okay, so I must get this relation. So can I derive the contraction from here? Oh yeah, sure, absolutely. Because since A to the K is a Markov matrix, so every entry of A to the K is clearly bounded. It should be a number between 1 and 0, 0 and 1. And since V is a unit vector, so this guy is also bounded. But so the left-hand side is, so every component of the left-hand side is clearly a bounded number between 0 and 1. But on the other hand, since the magnitude of this guy was assumed to be greater than 1, so therefore, this guy just carries over, but the therefore, there can be some, if k is a sufficiently large number, then some of the entries on the right-hand side can be greater than 1, right? So which is clearly contradiction. Okay, number 3. So I had trouble proving the theorem, the last part of the theorem. So, well, actually I can prove this, but well, I was not able to find some easier way to explain why number 3 must be true. So please allow me to omit the proof of the final statement. Sorry. So if you're interested in the proof of this, then maybe you can register yourself in the stochastic process course. Okay. All right. Also, there is a slide. There is a definition. Suppose that I have this given differential equation of degree 1, and we say this differential equation is stable if every eigenvalue, the magnitude every eigenvalue has a magnitude less than 1, and neutrally stable means some eigenvalues have the value, so magnitude equals 1, and the other eigenvalues has magnitude less than equals to 1. So this is what it says, neutrally stable, and unstable if there is one eigenvalue whose magnitude is greater than 1. So there is a immediate correlative. If A is stable, then this matrix tends to 0 matrix, because every eigenvalue tends to 0, therefore everything just stabilizes. Okay. So I don't have enough time, but I will try my best to explain the last example. So let me also, this time I will pretend myself to be an economist. So suppose that you have some hypothetical small toy example of economy model. So well, you know, in order to produce gas, then you need just a little bit amount of gasoline. Why? Because in order to produce gas, then you have to go to build the oil rig, and you will need the gas to send a ship to go to the oil rig and transport the gas. So in order to produce a gasoline, then you will need just a slight amount of gasoline. And same is true for the human labor. So in order to produce a human labor, then first you have to raise your kid, and raising kid requires a human labor, right? So the Leontief model goes like this. So let me consider this. There is a product number one, and in order to produce 1 unit of product one, then it takes this much of product number one, and this much of product number two, and this much of product number three. And to produce the product number two, 1 unit of this, then you're going to require this much other product, and for product three, and it's the same thing true. So the point is that in order to produce something, then you will need to consume something. Okay. So these numbers mean the consumption, and this is the production. Okay, so summarizing this, in order to produce the P1 unit of product one, then you will need, since in order to produce 1 unit of this, then you're going to need this much. Therefore, in order to produce P1 unit of product number one, then everything has to be multiplied by P1. Okay, so to produce P1 unit of product one, then you're going to need this much product, and to produce product number two, P2 unit, this much of this, then you're going to need this, you're going to need this much, and you're going to need that much. Okay. Okay. So, okay, now you know the game. So after all, so we have produced P1 unit of product number one, P2 unit of product number two, and P3 unit of product number three. So this is the number of units that we gained after one turn. And this is the number of product that we lost during the production. Okay, so gained minus lost. So this is what we call the net gain. And this matrix is called the consumption matrix, because as the name suggests, this implies the consumption of the product. Okay. And the question is, suppose that there is an external demand. Well, some sort of dictator or something, some governor requires you to produce this much unit of product number one, and product number two, and product number three. Can you do this? Well, if your economy is not working, then probably you might need more product than you can actually produce. In that case, your economy is doomed to collapse, because even if you struggle to produce more and more, eventually you're losing product. So therefore, your economy cannot sustain it anymore. So the question is, in order to meet this external demand, which I will call B, then you are supposed to solve this equation. This is the net gain minus the consumption should be equals to B. So in other words, can you solve this equation for P? If you can solve this equation for P, then your economy is not doomed. Your economy can go on. But if not, if you cannot find any solution, in other words, if this matrix doesn't have any if this is not an invertible matrix, then your economy will not be working and will be doomed to collapse. There is actually a very interesting idea. If is invertible, then I minus A inverse is I plus A squared plus A to the third plus dot. should be like this. Agreed? Do you realize why this one has to be true? Because if you multiply I minus a times this guy, then this is going to be this one minus a squared minus a. Okay, so it must be identity. So this is the reason that why this guy is the inverse of this one, if it exists. Okay, but is this guy always exist? This guy exists only if the matrix, the consumption matrix A is a stable matrix. So being able to find the solution or the future of your economy depends on the stability or instability of your consumption matrix. That is the key point of the Leon TX economy model. Okay, this is for today and see you next time. Bye. 아, 참, 거기 다음 주 화요일은 수업 없는 거 아시죠? 그리고 다음 주, 저 미안한데, 원래 다음 주는 수업이 없어야 정상인데, 제가 이제 우리 1반은 다음 주에 수업이 한 번 있더라고요. 그래서 1반의 진도가 뒤지면 안 될 것 같아서 정말 너무 죄송하지만 수업은 할 거예요. 그런데 출석은 저는 출석할 거니까 안 들어오셔도 전혀 상관없다. 미안해요. 네.
부모가 들어간 것 같은데.
아, 맞아요. 빠져야 돼요. 맞아요.